Yeah, it's fine. Approximation is fine. Okay, so we'll continue with our discussion about diodes. So we looked at the background where we talked about the device physics. From now on, we'll look at, well, I'll talk a little bit more about device physics just in terms of the equation, diode equation, and then we look at a few circuits involving diodes. So what we're going to look at is not inside the component, but now outside the component. We're going to take the diode as it is, and we're going to build circuits with the diode. So what we're interested in is the terminal characteristics of the diode, right? So you have two terminals, you have a cathode and an anode. If the anode is higher potential than the cathode, it is forward bias, diode is on. If the cathode is at a higher potential than the anode, diode is reverse bias, diode is off. And those are the points we will use to actually analyze our circuits. Okay, so going forward, you will learn a little bit about diode, a little bit about device physics, even with transistors and FETs, and then we will look at terminal characteristics, how the terminals behave, or how the device behaves at its terminals. And so that is what we're going to do next with the diode. So let me. Yes, I am. Thank you. That was one reminder. I think online students can actually remind me too, because they get the notification, right? The meeting is now being recorded. So in case I forget, I have two helpful students at either end on the front row. All right, ideal diode model. I think we solved a problem on this one. Does anyone have any questions about this? I think we rushed through it a little bit, so some students did have some questions. More likely than not, this might be on the next quiz. Okay, if you have any questions, I was going to say hold your peace forever, but I'll be available in the office hours if anyone has any questions. All right, there's another model. It's just the offset diode model. It is just something that I want to show students. It's basically similar to the ideal diode model, but it includes the 0.6 volts or 0.7 volts of diode voltage drop. Okay, we won't actually solve any problems with this, but this is a model that students should be familiar with. There is also a piecewise linear model where we divide the diode characteristic into pieces, and then each piece is linear with respect to time. And so we call that as a piecewise linear model. And in that model, it is similar to this one. So again, piecewise linear. And it is similar to this model where you have a resistor .6 or 0.7 volts. Oh, by the way, you'll see this discrepancy often. If you look at one textbook, it might say 0.6. If you look at another book or another researcher, they might use 0.7. The standard accepted practice for a silicon diode is between 0.6 and 0.7. Okay, 0.6 and 0.7. So piecewise linear model basically has a diode resistance in the forward bias. We call it RD, and then it has a voltage source or a battery of 0.6 volts. So basically, wherever we had the diode on or off, this 0.6 volts would need to be accounted for, which basically accounts for the threshold voltage that is required to turn on the diode, right? So piecewise linear model or the offset diode model requires that voltage offset. Again, concept that students should be familiar with. Okay. I won't test separately, or I won't test on specific problems. That makes sense, right? No, it's not something. It's pages. Why is it not going here? Okay, for some reason. Oh, it's considering page 27 is not part of the slide itself. Okay, doesn't have any arrows. Okay. So there are, again, with regards to device physics, there are many equations and many models that we can use to actually approximate and understand device operation. And depending on the surrounding pressure, temperature, the free electrons that are available, lots of variations can take place in the device operation. And this is true for in general for all semiconductor devices. Okay. So one of the most popular equations to actually describe a PN junction is known as the Shockley equation. Okay, Shockley equation. Shockley was one of the scientists, researchers who was involved with actually creating the first solid state transistor. Okay, and so the equation was something that he came up with, named after him, Shockley equation. It's also sometimes known as the diode equation or Shockley diode equation, but that's where it comes from. Now, typically, if I was teaching this for an E major class, we would do lots of problems involving this Shockley equation, but I tend not to do that for non-E major classes. I feel for a 10-week quarter, it's just a bit much. But again, it's something that students should be familiar with. If someone tells you about the Shockley equation, or as an engineer, if somebody's talking about it, this is what they're talking about. It basically states the diode current ID can be described by this equation. You have IS, which is the saturation current, the current that is very, very small due to the flow of minority carriers. E, exponent E, VD over N VT. And then -1. VT is the diode voltage. N stands for emission coefficient. It has to do with how the diode is fabricated or how it's manufactured, usually in the range of 1 or 2. IS, as I said, was saturation current. VT is described as a thermal voltage. Again, electrons have energy. When the temperature increases, the electrons can receive more energy and can flow more freely, depending on what kind of material we're talking about. And so the thermal voltage is taken into account. Thermal voltage is given by this equation, KT over Q. K is the Boltzmann's constant. T is the temperature in Kelvin. And Q is the charge of an electron in coulombs. So there's, again, lots of parameters in here. Every tiny thing does affect diode operation. Okay. Again, Shockley equation under certain conditions will approximate the functioning of a diode, functioning of a diode voltage versus its, functioning of the current versus its voltage. Okay, so ID describes the diode current. Again, it's something that students should be familiar with, so I like to talk about it in class, but I do not do any specific problems. If someone does want to go further into this, I'd be more than happy to talk to them outside of class. Yes. No, it will increase under most conditions. Yeah. Okay. Now let's take you back to E201, E201. What does VP stand for? It's right there. Peak voltage, right? What does VP-P or P to P stand for? Peak to peak. I already give the answer. Or VPP. What does VM stand for? VM? No. If you took my 201 class, the textbook we use, no, RMS is separate. Nope. That's RMS. That's different. What is on the y-axis? Well, what's on the x-axis? Time. Forget about pi and 2 pi, but x-axis is always time, right? What's on the y-axis? Well, voltage, but what if it's current? A smart A answer. What quantity are we talking about? Amplitude. What was the other word for amplitude? Magnitude. So VM stands for magnitude. Sam, you had the answer, but you were hesitant to speak up. Why? I wasn't gonna like give you a negative bonus points or negative penalty points. Sorry. So VM, the book that I use for my classes, Hamley uses M for magnitude. If you took a class with Professor Botros or Chinichian, he's a retired professor, and then Steve Dunton, they use Rizzoni. Rizzoni is probably going to use VP, but it means the exact same thing. It tells you the quantity in the y-axis. Okay, so VM or VP stands for the magnitude or the amplitude or the peak value of that waveform. And it's only describing one peak, not two. So if you want both peaks, you use VP dash P or VPP, peak to peak. So not going to get rid of 201 that easy, right? RMS, because it is the root of the mean of the square of the waveform, RMS. If we take average of a perfectly symmetrical AC waveform, the average will always be 0 because it is simply adding up all the instantaneous points in that waveform, right? So if you take the average value of AC waveform, it will always come out to be 0. So in order to describe the pseudo average value, we take the average of the square of the waveform. And because we take the square, then we take the square root at the end. And hence we come up with the RMS, the root of the mean of the square value of the waveform. Now, why are we doing all of this? Is because we are going to study rectifier circuits, diode rectifier circuits. Okay. So RMS value of this kind of AC waveform is going to be 0.707 or 70.7% of the peak value. Don't worry about the average value for now. We'll discuss the average value in just a little bit. Yeah, it started doing it again. It didn't do it even once in the morning. Okay. All right. Any questions? Hopefully everyone remembers this, or if not, at least this refresher was enough for everyone, right? Yeah. AC is one of AC analysis is one of my favorite topics. Well, not everyone enjoys it, but this is really nuts. Yeah, reactive power. Okay. So diode rectifier circuits, what they do is they actually rectify the AC waveform that we have from our power outlets into DC, usable DC. So all of the electric and the electronic devices that we use, they mostly run on DC. Whether you have your cordless phones, even I've even seen some small appliances that would run on DC. Not a whole lot, but some of them. Your laptops, televisions, all electronics, everything runs on DC. So that's why we had those what are now known as wall warts. Anyone hear of that term before? Wall warts is basically those adapters that you plug directly into the wall, kind of like square in shape, like a cube, and really very heavy. And the reason they were heavy is because they had a transformer inside. They especially used to come with like cordless phone sets. Anyone ever seen those? No one? No, it was just, it goes directly into the wall. And used to be like really, really like big ones. So I'm trying to think. Apple chargers, they used to come with like a cable, or they used to come with like a 2-pin prong that you could just plug directly into the wall. And you're familiar with those? That's yeah, that's essentially what it was. You plug it directly into the wall, you have a cable coming out, you have DC voltage. So takes the AC from our power outlets. The transformer is 2 inductors with the magic of mutual inductance. It steps down the 100 volts or more than 100 volts AC somewhere to around, well, depending on what we need, somewhere around 15 or 16 volts AC. Yes. Wattage. Also, the laptop adapters, they have a few extra there's a lot of other circuitry built into it. Yeah. But for the most part, yeah, it's just all the other chargers have to comply with the USB spec. So USB spec states that it cannot be more than 5 volts. Some of them go up to like 5.1 or 5.2 volts, but for the most part, they are like just around, they are 5 volts. So all USB devices can be charged with any kind of adapter. The only difference is how much current that adapter can supply. So like fast charging, for example, right? I think I might have mentioned this before. Fast charging, all it really is basically you're just drawing a little bit more current from the wall outlet. So you could take your smartphone charger and you could charge your tablet with it, but it's not going to charge as fast. The tablet's going to say, you send me like 2 amps of current. Your smartphone charger should be smart enough to say, I can only send you 1. If I send 2, I'm going to burn out. Okay. And that's the reason why manufacturers will tell you not to use like generic chargers. Like even generic chargers are smart enough nowadays, but if you buy like a really cheap one, from like Amazon or eBay, and if the circuit's not designed very well, if you connect your tablet to it and tablet says, I'm fast charging, I need 5 amps. The charger can only supply 2, but it will send 5 amps. What will happen? Overheat and explode. So that's why they say only use that. Conversely, if you use a tablet charger for like a smartphone, it should work just fine, because a tablet charger can supply, like say, maybe 10 amps, let's just say. Your smartphone only requires like 4 or 5. That's absolutely fine. Anyway, so we have a transformer. It steps down more than 100 volts all the way down to like 16 or 15 or 10 volts. Or if you're talking about 5 volts DC, it's going to step it down all the way to like maybe 7 or 8 volts AC. It's still AC, it's mutual inductance. This is also the working principle behind wireless charging. Nikola Tesla, the one that actually came up with this, well, not him alone, but he was the primary driving force behind that concept. You have a coil, inductive coil, in the back of your smartphone or your smart devices, and you have this wireless charger that has a coil inside it. When you take your smartphone and you place it on top of that wireless charger, the inductive coil in the charger and the smartphone, they link up. So the magnetic fields actually link up, and it transfers that magnetic field induces a electric current inside the coil of your smartphone that's converted into electric current, and that charges the battery. That's kind of like the principle behind this transformer. In a transformer, though, the 2 coils are in physical contact, and depending on the number of turns of the coil, it can be step up or it can be step down. So again, this is an entire separate field in electrical engineering. Anyway, so we step it down, we connect it to a rectifier circuit. This rectifier circuit is what we're going to study, which is diodes. And then once it's rectified into AC, we do some filtering, we do voltage regulation on it, and then we give it out to our load. This load could be anything, could be a laptop, smartphone, could be anything. Okay. Did all of that make sense? Okay. Yes. Right there. Why it only does it here? Is someone messing with me in this class? It only happens in E321. Doesn't happen in the mornings. I mean, I teach for like 2 hours in the mornings. Yeah, they said it wasn't, but again, I have no idea where or how it's connected. Well, they told me it's unplugged, so I have no idea where it's connected though. That's the thing. I don't why I don't know. Maybe the projector might. No, that's the Epson projector thingy. I don't know. Yes, for some, yeah, it seems like it's connected. Yeah. Okay, let's hope it doesn't disturb us any longer. We just need to last it for a few more minutes. So we have, what is I going to show? Oh, yes. Thank you. So right here, bridge rectifier. That's the one. So the property that we're going to use is the one-way street property of the diode, right? Positive half cycle, it works. Negative, it doesn't. So it's only positive. And that's where the most of the magic happens. The rest of it is to give you like as close to a flat line as possible. So depending on how many diodes or how many cycles we want to rectify, we have two primary kinds of rectification systems. We have a half-wave rectifier and we have full-wave rectifiers. Half-wave rectifiers are so called because it only contains one diode and it only rectifies half the AC waveform, only the positive half cycle. Okay, full-wave rectifiers have more than one diode and it will rectify both the positive as well as the negative half cycle. So this is the positive half cycle, positive half cycle, and this is the negative half cycle. So a half-wave rectifier only rectifies one half of the cycle, either the positive or the negative. So if we connect it to a voltage source, and let's say this is D1, that voltage source will be positive here. Let's do it this way. So in the positive cycle, the voltage appears like this. You get a plus here, you get a minus here. So the anode is applied a positive voltage, cathode is applied a negative voltage. What happens to the diode? On or off? Diode is on. D1 is on. If D1 is on, it conducts the electricity, it allows current to flow through. And if this is our input, we get that at the output. So that is what is being shown here. Right? So diode is on here and off here. In the negative half cycle, actually, let's take this out. In the negative half cycle, the electrons reverse, voltage polarity is reversed, becomes minus and plus. So the diode is now off. And because it is off, this is minus, this is plus, cathode is at a higher potential. current cannot flow through. And so there is no transmission of any kind in the reverse bias. And so only half the wave is being received at the output. So this here on the left shows you the input source voltage. This here shows the output load voltage going to your load. Okay. If it's an ideal diode, we assume that there is no threshold voltage required, right? So if you give an input of 7 volts, you get an output of 7 volts. But in a real life circuit, if you have one diode and you give 7 volts, well, 0.7 is going to be deducted from there in order to turn the diode on. And that is displayed by this dotted lines or dotted curve right here, marked as the actual diode or real life diode. So it accounts for threshold voltage. If you connect the diode in the other side of the circuit, the negative half cycles of the waveform will be rectified. You'd still get the exact same waveform at the output, but now the positive half cycle, the diode's off, and the negative half cycle, the diode will be on. Yes. Sorry, what? Offset diode counteracts. Oh, it accounts for the 0.6, 0.7 volts. Yes. Yes. Because that is the voltage that is required to turn the diode on. Yeah. Okay. Does the circuit make sense? Right? In half wave rectifier, only rectifies half the way. Now you may ask, this doesn't look like DC. And you'd be correct. It doesn't look like DC, but it's at least going in one positive direction. It's not going back or it's not reversing like AC. It only has positive peaks, right? So for a device, sure, the voltage is interrupted and it's very inefficient because it's only like, just a little bit of the actual signal is coming through. So it seems it's very highly inefficient, right? And that is absolutely correct. That's why this model is not very preferable. We used to find these kind of circuits in very cheap devices or very cheap adapters, but diodes, even just by themselves, cost just a few cents. So they are not that expensive. So next class, we'll look at some equations governing half wave rectifiers, and we'll look at full wave bridge, and full wave center tap rectifiers. Okay, we'll end class here today. I'll be in my office. I teach again from 3 to 6. So if you have questions and you want to stop by and see me, I'll be more than happy to. Yes, Wednesday. Well, Tuesday is even worse. Tuesday, 8 to 11 in the morning, 11 to 12 department meeting, and 12 to 3 in the clean room. So, yes.
Steve, I know last quarter I asked about having the canvas rearranged weekly or something instead of by assignment type, and you said that however you have it organized, students will complain about something.
Say, wait. Start at the beginning.
Basically, last quarter I asked you to arrange the canvas page by each week instead of each assignment type or something. And you said that you had it previously arranged like that, and then people would complain about it being set up like that. Similar, you're talking about how you have assignments that people skip, and then it doesn't put a grade, and then when you input the 0, then it lowers the grade. So with the current system, I have about 56% in the class, which gives me no idea. It's really because I haven't submitted anything except for the homework, and I have 180% because of the extra credit. So I have no really understanding what my grade means right now, which I feel like is much less effective of a grading system than students who skipped assignments. Kind of not understanding the grade at the end of